Hello everyone, I'm Kaixin Sui from Tsinghua University. Today I'm going to talk about characterizing and improving Wi-Fi latency in large-scale operational networks. This is joint work with collaborators from Tsinghua University and Microsoft. Nowadays, real-time and interactive applications have become very popular, such as instant messaging, web, and online gaming. These applications have strict requirements of latency to provide satisfying performance. The latency of mobile devices include wired part and wireless part, while the wired part is well engineered and has relatively stable and low latency. The Wi-Fi part can be affected by many factors, such as Bluetooth just mentioned by the last presenter. So Wi-Fi latency is often unpredictable and occasionally high. Since Wi-Fi hop latency can be a key bottleneck for latency-sensitive applications, in this work, we would like to answer the following questions. How is Wi-Fi latency? How related factors impact Wi-Fi latency? And how can we improve Wi-Fi latency? To answer those questions, we propose a system, Wi-Fi SEER, for measuring, modeling, and improving Wi-Fi latency in large-scale operational networks. So this is the overview of Wi-Fi SEER. Wi-Fi SEER is designed to work with enterprise Wi-Fi network. We call it EWLAN for short. The enterprise network provides Wi-Fi service for large-scale areas, such as the contact center. Actually, you are using the enterprise Wi-Fi networks now. Look up to the ceiling, you will find some enterprise APs here and there, and thanks to them, you can enjoy your Wi-Fi access now. Okay, let's go back to Wi-Fi SEER. At a high level, Wi-Fi SEER contains three parts. First, it collects Wi-Fi latency and related factors from the enterprise Wi-Fi network. Then, Wi-Fi SEER takes advantage of machine learning techniques to build Wi-Fi latency models from the dataset we collected. I believe you have already heard some guys talking about the magic of machine learning before. At last, based on those models, we have three typical applications in Wi-Fi SEER to help improve the Wi-Fi latency. Okay, next, I will introduce the detail of Wi-Fi SEER. First, let's take a look at how it collects Wi-Fi latency-related factors from the enterprise Wi-Fi network. To do this, we use a widely available data source, SNMP data. In general, enterprise wireless vendors, such as Cisco, measure a lot of Wi-Fi performance data by their access points and wireless controllers. So we collect those data from the wireless controller every 1 minute through SNMP. After looking into the SNMP data, we determined to collect three types of factors, including 11 radio factors, like channel utilization, 3 protocol factors, like the channel number, and 6 external factors regarding time, location, and hardware characteristics. Next, I will introduce our method Ping2 to measure Wi-Fi latency in the enterprise network. Someone may ask, why not just get latency from the SNMP data? This is simply because wireless vendors typically do not monitoring the latency in their enterprise devices. Beyond that, there are another 3 challenges for measuring Wi-Fi latency. First, sniffer-based methods require deploying extra wireless sniffers. They may be feasible for a small network or test bed, but they are inconvenient or too costly for large-scale networks with more than thousands of APs. Another way is modify the hardware or firmware of APs to let them support Wi-Fi latency measurement. However, this solution cannot be used immediately in enterprise network because it usually takes a long time for vendors to adopt them in commercial networks. And last, for the sake of battery, mobile devices are often in energy-saving modes and need extra time to wake up to respond to measurement tools such as ping. This will significantly inflate the naive ping latency and make it inaccurate. To solve these challenges, we propose a method called Ping2, which can measure the Wi-Fi latency actively in a large enterprise Wi-Fi network at low cost, without deploying sniffers, without any modifications of the existing APs and user devices, and can measure the sleeping devices more accurately. Ping 2 is an active measurement method. It only needs to add a server into the network. And this server will run Ping 2 to measure the Wi-Fi latency of mobile devices in the network. To understand how Ping 2 works, let's first introduce why NIU Ping doesn't work. We know that mobile devices are often in energy-saving mode if itself do not have any workload. If we try to ping a device in such a case, we need a lot of extra time to wake up the device, which will cause the RTT significantly inflated. So it cannot measure Wi-Fi latency accurately. Our idea to solve this problem is quite simple. Although the first ping may not give us an accurate result, it can wake up the device. Therefore, if we immediately send the second ping, it will avoid the energy-saving mode and in most cases and measure Wi-Fi latency more accurately. So this is how Ping 2 works, using the first ping to wake up the device and the second one for measurement. Also notice that because the distance between the Ping 2 server and the APs are very short, the wide path latency is very low. For example, the 99th percentile is less than 1 millisecond in Tsinghua campus, so it is negligible. Ping 2 measures the Wi-Fi latency of all the devices connected to our Wi-Fi network every 10 seconds. We get the IP addresses of those devices also from the SNMP data. We evaluate several aspects of Ping 2. It has low battery cost of devices and turns out to be accurate and lightweighted. So we deployed the above two measurement methods, Ping 2 and SNMP data collection in Tsinghua University to get 1 week data set. Tsinghua University covers an area about 4.2 square kilometers with more than 2,700 access points deployed in more than 100 buildings. In our data set, there are more than 47,000 different mobile devices appeared. Based on this large Wi-Fi latency dataset, we made several observations. First, we find that Wi-Fi latency follows a long-tail distribution. In particular, while the median is only 3 milliseconds, the 90th percentile is 20 milliseconds, and the 99th percentile can be as high as 250 milliseconds. So how these high latencies will impact application performance and user experience? Take web service as an example. According to previous studies, 20 milliseconds last mile latency can be amplified into 3 seconds of web page load time, and this is slower than 47% of users' expectation. So our measurement shows that Wi-Fi latency is not good enough in the wild. We also notice that Wi-Fi latency under 5 GHz is lower than 2.4 GHz. Then we find that this can be caused by overutilized 2.4 GHz. We see that the channel utilization of 2.4 GHz is much higher than 5 GHz. However, in Tsinghua University, the dual-band devices that is supporting both 2.4 and 5 GHz are 1.6 times more than the devices that only support 2.4 GHz. Also, the network operators turn on the band steering policy of Cisco devices, which is designed to make 5 GHz more attractive. Given these two facts, why 2.4 GHz is still overutilized? We find that devices have their own ways to select AP and band, usually RSSI based. This makes the band steering less useful. So we can see that different vendors will not collaborate well, and this problem can cause some solutions failed. To solve the problem of overutilized 2.4 GHz, of course, we cannot tell so many vendors to collaborate together, but we can do something else. Our solution is adding a 5 GHz only SSID in Tsinghua campus, so users can manually choose 5 GHz by connecting to this SSID. This simple solution gives users an opportunity to use those less crowded bands, and it turns out to be very effective to balance the traffic between 5 GHz and 2.4 GHz. Please see our paper for more details. In addition to band, we find that the relationships between Wi-Fi latency and related factors are also complex. Some of them are non-linear or even non-monotonic. One potential reason for those complex relationships is that different related factors are independent with each other. Our dataset demonstrates that this is true. For example, SNR positively and strongly correlates with RSSI. Based on the above analysis of our dataset, we see that Wi-Fi latency is not good enough. So how can we improve it? We give 3 typical applications for this purpose. The first one is to understand the effects of radio factors on Wi-Fi latency, which can help vendors or protocol designers to make better decisions in their designs. The second application is to help operators diagnose high Wi-Fi latency in their own networks. The third one is to help mobile devices select a better AP with low latency. We find that all these applications require models that quantify the relationships between different factors and Wi-Fi latency. For example, in application 3, with such a model, we can use measurable factors to predict which AP can provide low latency. However, our earlier data analysis results with several challenges for building such models. For example, Wi-Fi latency is affected by so many factors, and the relationships are so complex. So how to model those complex relationships? We take advantage of the machine learning techniques. Machine learning is well known for being able to model complex relationships through a data-driven way. In particular, we use supervised machine learning approach to build classification models of Wi-Fi latency with different related factors. And these models play the key role for each application. However, you know that different applications have different requirements regarding the models. That means the models cannot be built once and for all. So we tailor the model for each application. Different aspects of the model are designed accordingly. For example, a user should be able to understand the model of application 1, so we select an interpretable model, decision trees, for application 1. In contrast, application 3 only needs to predict as accurate as possible, so we choose a more accurate model, random forest here. After introduced the key idea of how we build models, next I will talk about application 1 and application 3. Since I don't have much time, I won't go into application 2. If you are interested, you can find all its details in our paper. In application 1, we build this decision tree from our dataset to correlate industry standard radio factors to Wi-Fi latency. With this model, we can learn the radio factor effects on Wi-Fi latency. For example, since the decision tree puts important factors near the root, channel utilization is the most important factor for Wi-Fi latency among those radio factors we collected. In particular, most slow and extremely slow latencies happen when channel utilization is higher than 47%. That is on the right side of the tree. This issue is considered as heavy load problem. Besides, we find that when channel utilization is relatively low, say in no more than 22%, there could still be some slow conditions. These conditions are caused by too many devices connecting to the same AP, which will lead to the local contention problem. Last, we see that low SNR, less than about 21 dB, will cause high latency. This is known as the fading and noise problem. The above are some highlights and insights we get from this decision tree, and they can be used as guidelines to help vendors, researchers, and protocol designers to make better decisions. Okay, next I will introduce application 3, selecting a low latency AP. We know that devices commonly use RSSI to select which AP is better. However, surprisingly, we cannot find RSSI in the tree that was built in application 1. Does this mean RSSI is not that important? The answer is that RSSI is indeed not that important for predicting Wi-Fi latency, especially when being considered together with the channel utilization. For example, this figure shows that for a given utilization, no matter how high or low, latency does not change obviously along the RSSI. So here comes the question. Since Wi-Fi latency is affected by so many factors and only using existing client-side information is not enough to make the right choice, make the right decision, how can we select a good AP for low latency? I will use an example to show the key idea of how we select a low latency AP in application 3. First, we intend to help those devices experiencing the high latency. To this end, we will collect Wi-Fi latency-related factors of the APs near the device. These factors will be input into our Wi-Fi latency model, and it will predict which AP has the lowest latency nearby. Then it will inform the device to connect to that AP to have a lower latency. This is the key idea of our solution. But building such a system is not that easy. We need to decide how to control the AP selection behaviors of devices. Ideally, it should be implemented at the operating system or protocol level. But however, these designs are very difficult to deploy at a scale and evaluate it immediately. So at last, we choose to implement it at the application level. That is, we developed an Android application and use the Android API to connect the device to the given AP. In this way, we built our application called Edge, associated to good enterprise APs. It works as follows. First, the device sends APs nearby to the Edge server. Then, the Edge server will collect factors of each AP and use our model to predict which AP has the lowest latency for the device. The Edge server then will send the AP decision to our Edge application installed on the devices, and then the app will associate the device to the AP specified. Our Edge application is installed and used by over 1,000 devices for 2.5 months, and the results shows that after its association to the suggested AP, 92% of their latencies are reduced, and 72% are reduced by over half. And here comes the conclusion. First, Wi-Fi SEER is a general and practical system for measuring and improving Wi-Fi latency. It explores machine learning for modeling Wi-Fi latency. Wi-Fi SEER has been deployed at a large scale in Tsinghua campus. With the results of Wi-Fi SEER, we made several observations which lead to 2 deployed approaches, adding 5 GHz only SSID, and you can see another one about dense deployment in the paper. As for future work, we can explore similar methodology on other performance metrics, such as throughput. AP selection when implemented at app level can be further extended to operating system or protocol level. At last, in the end of this year, Tsinghua campus will deploy another 7,000 APs. This growing environment will provide more research opportunities. If someone is interested, we can talk offline. Thank you.